Good afternoon, everyone, and welcome to this hour-long webinar brought to you in association with COMSOL on the topic Improving Electric Drivetrain Efficiency with Multiphysics Simulation. As we all know, the performance of an EV is largely dependent on the performance of its electric drivetrain, and improving the efficiency of this drivetrain involves addressing an interplay of several phenomena of physics, such as electromagnetics, vibrations, heat transfer, and solid mechanics. Therefore, multiphysics simulation plays a crucial role in modeling such phenomena and enabling an agile process for the R&D of electric drivetrain components. Over the course of the next 60 minutes, this webinar will help you understand how to better use modeling and simulations to improve electric drivetrain efficiency. To tell us more about it with a detailed presentation, I would like to invite Mr. Sharad BN, Technical Specialist, COMSOL. Sharad is part of the applications team at COMSOL India. He received his master's degree in machine design from BMS College of Engineering, Bengaluru. In his previous experience, he comes with an experience of mechanical integrity assessments of gas turbines at Siemens. Before I hand it over to Sharad, I would like to request the audience to kindly put your questions in the Q&A box, and we will take them up once the presentation gets over. Over to you, Sharad.
Yeah, thank you, Mayank, for the kind introduction. So, in the interest of bandwidth, I'll be, switching off my video, and I'll have just the audio. Yeah, can you please confirm if my screen is visible?
Yes, Sharad, you're good to go.
Yeah, thanks, Mayank. Yeah, good afternoon, everyone. So first of all, on behalf of COMSOL, I would like to thank everyone for showing interest in today's webinar session on improving the electric drivetrain efficiency with multiphysics simulation. So if we ask ourselves why multiphysics, right? So let me start off with an example. So let us start off with the example of modeling an electric motor. Right? So first, we start off with the performing the electromagnetic analysis, right? But extracting torque from the motor generate losses in the form of heat, and this results in temperature rise, and this in turn affects the electromagnetic characteristics of the motor. Right? So here we'll have to couple electromagnetic analysis with the thermal analysis to check the temperature rise. Right? And to analyze the various cooling methods, right, that are needed for thermal management, so we'll have to couple electromagnetic, thermal, and fluid flow. So, and let us say there are non-uniform gaps between the stator and rotor, or due to other imbalances, and so this can cause electromagnetic force imbalances, and this can lead to noise and vibration in the motor. So this would need coupled electromagnetic, thermal, fluid, and structural analysis as well, right? So in general, real-world machines are multiphysics-based systems, right? And to predict the performance of the machine accurately, so we'll have to perform multiphysics simulations, and this would include all the significant physics. And in that sense, COMSOL Multiphysics provides an interface to couple two or more physics that affect each other. Right? And one major benefit of COMSOL is that so the user interface remains the same irrespective of the physics that are involved in your machine. So to briefly understand our audience today, let us start off with the poll question. Yeah, so probably you'll be able to see the poll question in front of your screen. So I would request you to select the appropriate answer. Yeah, thank you for answering the poll question. So let us move ahead. So presently we talk about clean and green energy, right, for electrification. Uh, this is mainly because in the conventional drivetrain, so we have the internal combustion engines, and these have the least efficiency in the drivetrain, right? And hence replacing the IC engines with the electric motors as prime movers for transportation can lead to a large overall increase in efficiency, right? This can be in any form of automotive applications, or it can be even in wind turbines, right? Or electric aircrafts, electric bikes, drones, among others. So in the subsequent slides, we will discuss the different aspects of motors that we can analyze and predict the motor behavior. So we essentially have two different kinds of electric motors. So broadly, so they are radial and axial flux machines. So permanent magnet motors and the induction motors that are used in the even the Tesla cars are conventional motors, which are of axial flux in construction, right? And COMSOL offers inbuilt features to easily analyze these radial flux machines. And axial flux motors are upcoming technology, and so its advantage is essentially higher power density and for a smaller size, right? And COMSOL also offers fundamental features to analyze so these kinds of new designs as well, right? So such as axial flux machines. And recently, you might have even heard of a startup in Bangalore that is using axial flux machines to basically move the trucks. So yeah, so coming to the feature set in COMSOL, yeah, so COMSOL has a rich feature set for motor modeling and has many examples in its application library. Right? So when it comes to electromechanics, so COMSOL can model electromechanical parameters, and you can extract parameters such as torque ripple, torque, it can be cogging torque, or it can be even stresses due to magnetostriction, etc. Right. When it comes to the thermal analysis, you can extract efficiency maps and temperature maps. Right. So these are essentially average efficiency and temperature of the motor for different torque and speed values. Right. Due to the various losses, be it hysteresis or eddy current losses, you will have to extract the various copper and iron losses as well. Right. And because of rise in temperature, so you'll have to even look at the various effects of demagnetization. Right? And this demagnetization is essentially a result of thermal effects, right, on electromagnetic performance, and this can be easily modeled in COMSOL. Right? Extending your motor analysis, you can even perform noise, vibration, and harshness analysis, right? And you can reduce the motor and vehicle noise and meet regulation parameters, or for increasing passenger comfort as well. And to further optimize your motor, you can perform various optimization studies, right, such as parameter, shape, and topology optimization. And here the objective may be to maximize torque or to minimize the mass of the various components of the motor, and hence the cost of the motor. We'll see a few examples during the course of the presentation as well. So we can, so there's an example of one such proof of concept model, right? So this, you can see the specification sheet here, and this essentially, what is typically used in the electric vehicles today. So typical power is around, 240 kilowatts and 460 Newton meters of rotor torque, so etc. So COMSOL has proof of concept models in its application library. And so you can basically look at these models in the COMSOL website as well. Right? And so, yeah, COMSOL also has a feature set, and where you can consider the effects of overhangs and effects of skews in the motor as well. These are basically the overhangs and effects of skews in the motor as well. So let us now try to understand what exactly you are trying to use COMSOL for, right, in the motor analysis. So yeah, so you should have the question in front of you. So we would request you to select the appropriate options. Yeah, thank you for answering the whole question. So before we start off with any simulation, so we need the CAD parts, right? So in console, you can either import the various parts from other, third-party CAD softwares into console, or console also offers a ready-made, part library where you can import the, 2D and 3D components of the motor as well for your analysis, right? So you can even prepare the geometry from geometric primitives, right? So COMSOL also offers feature set to model your geometry from scratch as well. Right? And these parts can be organized in libraries, and this in turn can be shared with your colleagues as well. So once we have the CAD parts, so the next step is to start off with the electromagnetic analysis. All right. So in this slide, we'll look at the dedicated features that are available in COMSOL for modeling an electric motor. So if you look at the magnet feature, so this is used to model the permanent magnet, and you can specify the magnetization direction, the magnet arrays, and so on. Right? So if you look at the multi-phase winding feature, so this is used to model the stator coil excitation pattern. And this feature essentially has options to assign the excitation pattern in such a way that it produces unidirectional torque on the rotor. And COMSOL also has features to extract the torque from the motor stator interface. So this feature has inbuilt variables to calculate the torque and the forces at the interface. So once you do the electromagnetic analysis, the next step is the computation of iron and copper losses in the various components of the motor. So for modeling the iron losses, so there essentially are three options. So we have the two, empirical formulations, so which are Steinmetz and Bertoldi loss formulations, and they allow you to model the effect of laminations as well. And the third option is you can use the user-defined option, where you can import the manufacturer data sheet, which has the loss versus magnetic fields to compute the iron and copper losses. Right? And in addition, you can also compute the time to frequency losses. These are essentially the time average losses in one electrical cycle. And you can even consider the effects of harmonics as well in this feature. So once you extract the losses, and these losses lead to rise in temperatures, right? And so, yeah, so for modeling the iron losses, so once you model these losses, due to rise in temperature, the copper conductivity will change, right? And so will the remnant flux density of the magnet. And hence the electromagnetic behavior here is affected by the temperature rise due to the different losses. Right? And here you can see the, the coil wire conductivity, which is a function of temperature here. And in COMSOL, one benefit is that you can also see the underlying equations, right, that basically affect the simulation results. And if I go to the previous slide, even here you can see the Steinmetz loss formulation here. Essentially, COMSOL is pretty transparent when it comes to what the underlying equations are. So here you can look at the different efficiency maps. And the efficiency map is basically, the motor efficiency as a function of motor speed and torque, right? So here in the first two maps, so here these two maps are without considering the effect of temperature rise. And the third map is obtained by fully coupled multiphysics analysis, where, the effect of temperature rise is also considered. And due to this, the copper conductivity and magnet's flux density also changes with temperature. And here you can clearly see that effect. Right? So, so for a constant stator current, the maximum torque is reducing with speed. And this can be seen in this third graph. Right? In addition to the efficiency maps, you can also, get the temperature maps also. So these temperature values are average stator temperatures as a function, once again, of speed and torque. And the map presented here is for natural convection. And these temperature maps can also be extracted for, forced convection, liquid cooling, and so on. And so one more thing is using these data points, the range of the vehicle can also be accurately predicted. Basically by coupling these data with the battery management software as well. And there are multiple blogs written on these topics. And so probably at the end of the presentation, I'll take you to the COMSOL website, and probably we can have a look at these blogs as well. So now we discussed the electromagnetic and the thermal analysis that can be coupled to the electromagnetic analysis for the performance evaluation of the motor. Right? So now let us look at one such user story. This is from Bosch. They are a long-term user of COMSOL Multiphysics. Right? So here the researchers have done, essentially a coupled electromagnetic and thermal analysis of a DC link capacitor, which is housed inside a inverter, right? So this inverter is essentially placed in between the battery pack and the motor in the drivetrain, right? And DC link capacitor is a crucial part of the inverter. And so basically its design is constrained by many parameters such as space and temperature, right? So in that regard, it can only withstand a maximum temperature rise of 105 degrees Celsius. And the researchers at Bosch did a coupled EM and thermal analysis where they included the eddy current effects and proximity effects as well. So they have essentially augmented their experimentation with simulation. And this has helped them cut down the prototyping time and help them bring the product to market sooner using simulation. All right, let us now see what further analysis you can do to your motor, right? So in this case, so it is essentially the noise, vibration, and harshness analysis. So basically in motors, vibration can be caused by shaft imbalances, right? Which may be due to non-uniform air gap or due to some other form of imbalances in the geometry. So this causes unbalanced electromagnetic forces as well. So this vibration can be analyzed by coupling the electromagnetic and structural analysis, where you transfer the force and torque data from electromagnetic to the structural analysis, and you look at the stresses due to those forces and torques. And here in this animation, you can essentially see the stress distribution in the housing due to the vibrations. So deformation also affects the electromagnetic behavior of the motor, right? So there's an example of a two-way coupling of electromagnetic and structural analysis, right? So the minute deformation of the stator affects the torque generated by the motor. So this deformation shown in the above, this animation is basically a bit exaggerated. But this deformation is computed in the structural analysis, right? As I mentioned before, the loads are transferred from the EM analysis to the structural side, and this is computed in the structural module, right, part of the analysis. And here you can also see the axial torque, right? So the blue line here is the torque extracted from the electromagnetic analysis, and the green line is due to the coupled electromagnetic and structural mechanics analysis. And due to the deformations, you can essentially see the higher torque ripple in the coupled analysis. Right? So for accurate, analysis, it is always, recommended to involve all the, significant physics in your analysis. So here we go a step further, right? So here we are basically doing vibroacoustics analysis. So due to the vibrations in the motor, so we are looking at the noise parameters as well, right? So here essentially we are doing electromagnetic, structural with acoustics analysis to predict the noise generated by the motor due to vibration. And on the right, you can also see the Campbell diagram. So this is essentially used to analyze the different frequencies of noises generated as a function of speed as well. So until this point, we saw that we could model the various types of motors, right? Be it radial configuration or the axial configuration. So in COMSOL, you can also analyze the linear motors, right? So linear motors are very much in focus these days due to applications like Hyperloop. And COMSOL allows you to model the linear synchronous and induction motors. So essentially by taking advantage of the symmetry. And the periodic condition is one such feature that is available in COMSOL. And it simplifies the modeling of such linear machines and reduces the modeling complexities. So here essentially one or couple of unit cells are included, ignoring the end effects of the linear motors. So until this point, we looked at the different physics that we'll have to include for accurately modeling the electric motors. Now let us look at how we can fine tune the end analysis, right? So this is essentially the optimization, and so COMSOL offers three kinds of optimization. So one is a parameter, shape, and topology optimization. Right, in parameter optimization, the geometry is fixed, but the various components of the motor is parameterized. So various parameters, geometrical parameters essentially. They can be, for example, thickness of the back iron. It can be the width of the teeth, or even the height of the magnets, etc. In shape optimization, the shape of the geometry itself is changed. And in topology optimization, so essentially the topology of the selected components is changed. So here you can see the animation of one such topology study of an axial flux motor. Right? And topology optimization can give unique designs for the stated objective. Yeah, and so the objective function of an optimization study can be to maximize torque or to minimize the mass, etc. And one advantage in COMSOL is that the objective function can come from any physics, right? So, for example, it can be torque when you're dealing with electromagnetics analysis. It can be temperature in the heat transfer analysis, or it can be stresses when it comes to structural mechanics analysis. Right? So the objective function can come from any of the involved significant physics. So let us now look at an example of a parameter optimization case, right? So here the objective is to maximize the torque output from the motor. And the control variables are, so the tooth width, back iron thickness, magnet width and height. Right? And as constraints, so we want the area of the coil to be conserved. So, and we are targeting a 10% reduction in the magnet size. So if we look at the results of the parameter optimization study, so there was essentially a 2.8 increased torque or power output while conserving losses. Right? So you can see the torque values here. So the blue line is for the initial design, and while the green line is for optimized study for the torque output, and the red line is for efficiency, optimized efficiency. Right? So here you can see that for the optimized output, there is a small drop in torque ripple as well with the higher torque values. So let us now look at, so here you can see the animation of the parameter optimization study. So essentially uh, basically different geometric, parameters have been varied to get the optimized torque output. So here, let us look at an example of shape optimization. Right? Here, the objective is to minimize the torque ripple and the deformation of the domain. Right here, the magnet domain. So you have the freedom to decide whether the deformation is to be free, that is in any direction, or only in a certain direction. Right? And if we come to the objective function, here it is to minimize the difference between the instantaneous value and the target value. So, right, this is essentially the torque ripple we are trying to minimize. And the control variable here is essentially the shape itself. And since this is a shape optimization study, so this is based on gradient-based algorithms. Now let us look at the results of the shape optimization study. And so yeah, here you can see the torque curves for the initial design, and the parameter optimized design, which is the green one, and the shape optimized study, which is the red line. Right? So here you can see there is a significant drop in the torque ripple rate compared to the initial design. Right? So the torque ripple has been reduced from 9.8 to 4.5%, right? Essentially 50% drop. And even the 12th order torque harmonic has also been reduced by more than 75%. All this while maintaining the motor average torque. Right? You can see the average value has been maintained in the optimized study as well as the initial design. And here you can see the animation of the shape optimization as well. So if you can see the animation here, you can see that the shape optimization essentially allows for a more free deformation of the geometry parts. Right? So allowing them to take on shapes that are not easily defined by geometric parameters. You can't define some of the shapes by geometric parameters. Right? In that scenarios, you can make use of shape optimization. Let us now see the topology optimization. Right? So here we are going to choose the same the 2D motor model that we had selected for the previous two optimization studies as well. Right. So essentially in topology optimization, here you can see that the material distribution itself is being changed here, that of the rotor, right? So essentially the optimizer is determining that the motor torque is least sensitive to high magnetic permeability near the shaft, right? So it is, I mean, the motor performance is independent of the magnetic permeability at the center of the rotor. So optimizer is determining that, and it is removing the material, magnetic permeable material from the rotor. And one more benefit of COMSOL is that the optimized geometry can also be extracted and exported as a CAD file, for any further analysis as well. Yeah, now that we saw the different optimization features that are available in COMSOL, let us now look at one such user that has made use of the optimization feature that is available in COMSOL. So here, so this is a user story by Volkswagen, right, based out of Kassel, Germany. So here, engineers have evaluated the strength of the rotor laminations. Right? This essentially the motor that is used in their very popular EV platform called ID.4, and they've also performed magnet optimization, basically topology optimization of the magnet. And so in that case, they were able to reduce the torque ripple by over 70% and magnet material by over 10%. So yeah, this is essentially one such example that demonstrates COMSOL's ability in producing novel designs while reducing the design iterations and also leading to faster times in getting into the market. There is also a very detailed blog that is available online. Probably, yeah, we can share those links as well after the presentation. Yeah, so let us now move on to a brief demo of modeling a motor in COMSOL. So here we'll look at how we can extract the coiling torque, right? So we'll also look at how we can extract the different losses in the motor using the time to frequency losses study step, and we'll also see how we can calculate the stator core loss as well. So yeah, let me quickly open up the COMSOL user interface. Yeah, once you open the COMSOL user interface, you'll be greeted by the model wizard. So here we can select the space dimension that we want to work in, either 3D, 2D, 1D, or even the lumped parameter analysis as well. So let us select the 2D. And here you can see the different physics that are available in COMSOL, be it the AC/DC, acoustics, electrochemistry, heat transfer, structural mechanics, etc. So COMSOL also offers the mathematics feature where you can model using your own equations as well. So let me open up the AC/DC module. That I'll open the electromagnetics and mechanics. And in that, we have dedicated feature, right, for rotating machinery. So once you add the physics interface, you can also see what the software will solve for, right, the dependent variables. Here, the dependent variables are magnetic vector potential and scalar potentials. So next step is to study select the study type. So here I will start off with stationary. So yeah, this is the user interface of COMSOL. So on the left, we have the model builder where you can see the different processes that are involved in building a model. So be it defining different parameters, or creating or importing your own geometry, adding materials, right, different boundary conditions, creating mesh, defining the study types, and in the end, visualizing the results as well. Right. So we have the same functions on the top as well in the form of ribbons. In the center, we have the settings tab for each and every individual nodes on the left in the model builder. And then finally, we have the graphics section. Right? Okay, so let us first start off with the geometry. So in COMSOL, you can either create your own geometry from scratch, or you can import from a third-party CAD software, or you can even import geometry from the part library that is already there in COMSOL. Right? So I'll go to parts, part libraries. Yeah, so in the rotating machinery 2D, so we have the different configurations of rotors. So be it the embedded magnet, V-shaped, or the surface mounted magnets. Right? I'll select the surface mounted magnet. And one advantage of importing the geometries in COMSOL is that it is parameterized, right? So once I imported the internal rotor, you can see the different parameters that have been already set. So you can see the number of magnetic poles here. So we'll have a 10 pole, magnet configuration. Then I'll click on build selected. So the next step is to import the stator. Under rotating machinery 2D, we have the stator parts as well. So the slotted external stator. I'll add this to the geometry. Yeah, so once again, the geometry is parameterized. So here you can see the number of slots, right, that you can determine based on your requirement. And click on build selected. Yeah, here you can essentially see the rotor and stator. And in our configuration, I'll select the this two winding slot configuration. So we'll change the slot winding to 2. Build selected. So essentially, this is a 2 windings per slot configuration. So for combining the geometry, I'll select at form assembly since there is a relative motion between the stator and rotor. So we have the geometry that is ready with us. So once we have the geometry ready, the next step is to add the materials to the geometry. So COMSOL has a large material library as well, or you can even import material from outside sources as well. Right? You can add a blank material and define the properties as well. So for now, I'll add material from the library. So here you can see that the materials have been categorized based on the physics as well. Right? So it can be AC/DC, battery, optical, piezoelectric, RF, semiconductors, among others. So first I'll add the air material, add to component. Yeah. So the next step is to add the soft iron without losses, which I'll add to the component. And I'll select the different soft iron components here. Basically the rotor casing, then we have the stator component as well. And moving on, we'll add the magnet material as well. Right? So we'll add the N42 sintered magnet here. And we can select the magnet domains here. Right. So we can see the soft iron components and also the surface mounted magnets that we have modeled. So we have added the materials as well. So the next step is to assign the boundary conditions to the different components. Right. So first we'll start off with modeling the iron losses. So for that, we'll right click on the rotating interface and we'll go to the magnetic fields and we'll add the Ampere's law. So this is to model the losses in different iron components. So here you can select the magnetization model as well. So yeah, if your component is linear, you can go ahead with the relative permeability. Or if it is you want to model the nonlinear magnetic behavior, you can select the BH curve as well. And to see the BH curve, we can go to the N42 magnet material. Right, and you can see the remnant flux density. The soft iron, and you can plot the BH curve as well. Right? Go to the BH curve interpolation. So here you can see the nonlinear material property as well. All right, now we'll add the loss calculation feature to this. Right? And under loss calculation, you can select the model that you would like to go ahead with. So we have the Steinmetz and Bertoldi, empirical loss formulations, and you have the user-defined option as well. And so for now, I'll go ahead with the Steinmetz formulation, and I'll leave the default, constant values. So now that we have modeled the, loss formulation, the next step is to model the magnets. Right? So what I'll do is I'll right click on the conducting magnet feature. Let's click on conducting magnet. Right. So here once again we'll have to select the various magnet domains. So I'll quickly select the magnet domains. Right. And the magnetization method. So there are different methods to this. So we'll go ahead with specify north and south boundaries, and the pattern type is circular pattern. Right. So for linear motors, it can be a linear pattern. So we'll go ahead with the circular pattern. Right. You have the different magnetization models as well. Recoil permeability, so electrical conductivity as well. So if you want to model the eddy current effects in the magnets, you can model the electrical conductivity as well. But in this example, we'll just ignore the eddy current effects in the magnets. All right. So we'll now define the north and south boundaries of the magnet, north and south poles of the magnet. Right. So we'll define the north poles for two magnets, and we'll define the south poles for the two magnets. And since the pattern type is circular, the COMSOL automatically, assigns the magnetic poles to other magnets as well. All right. So the next step is to model the winding, right? Coil winding. So for that, I'll once again right click on the rotating machinery feature, and then we'll select the multi-phase winding. So for this, you'll have to select all the the coil domains for this. So to reduce the number of clicks, what we can do is I click on the external stator. I'll go to the domain selections. Click on stator calls. Right? I'll just enable this feature. So this essentially creates a selection. So I'll go to the multi-phase winding, and in the selection, we can select the stator slots. Right? So yeah, so the multi-phase windings will be modeled in the stator slots here. So in our current demo, we'll keep the motor as an open circuit. So essentially what we are doing is we'll be, treating this as a generator, right? So we won't be giving any excitation current, right? And we'll just give it an input rotation speed, and we'll check the output voltages, right, from these windings. So essentially a generator. So we have different winding layout configurations as well, right? So in this, so we have the automatic three-phase. And once you click that, you can select the number of poles and number of slots in the in your motor as well. So in this configuration, we have the 10 pole slot, and we have 2 coils per slot, right? So I'll change this number to 2, and I click on add phases. So once you click on add phases, you'll see that there was automatically 3 phases added to the multi-phase winding, right? So you can see the 3 phases as well here. So we have modeled we have added the features to model the different losses. We have added features to model the permanent magnet and the excitation features as well, the multi-phase winding. So that the next step is to extract the torque out of the motor, right? Or in case of generator, it is to apply the torque. For that, COMSOL offers this RQ torque calculation feature, right? And so since we have defined the stator and rotor domains, uh, and we have defined the form assembly, right? So in the previous step here, so COMSOL automatically detects the interface feature between the stator and the rotor. So it has automatically selected the air domain interface between the rotor and the stator, right? And this is used to essentially extract the torque from the motor. All right, so now we have applied all the essential boundary conditions that are required to model the motor. And the next step is to discretize the domain, right? For that, we'll use the meshing option. So in COMSOL, you have 2 options to generate meshes, right? So it is essentially the physics controlled mesh and user controlled mesh, right? So in physics controlled mesh, COMSOL automatically creates a mesh depending on the different physics that are involved in your model. And in the user controlled mesh, you can individually control the mesh element size and types on each individual domain boundary or even the point. And also in the physics control mesh, you have the different types of element sizes, right, ranging from extremely fine to extremely coarse. So for now, we'll go ahead with the normal size, and I'll click on build all. So just to recollect, initially first we added the geometry, right? Right. So the rotor and the stator. Then we added the different materials that are there in the geometry. Then we added the various boundary conditions, right, to extract the losses, to model the magnets, to model the multi-phase winding, and to extract the torque from the rotor as well. Then we created a mesh from the model. And the next step is to define the study steps, right? So here we'll be doing a time-dependent study. So what I'll do is I'll right-click on study, go to the study steps. We have the different kinds of study types that you can add here. So I'll go to the time-dependent study types, and I'll add the time-dependent study type here. So yeah, and before that, what we'll do is we'll add the moving mesh feature. So yeah. So moving mesh is essentially needed when there is relative motion between the 2 domains, right? So in this case, the rotor is rotating. right? And the stator is, I mean, obviously stationary. So there is, we need to model the mesh in such a way that it takes into account for the movement, right? And in COMSOL, we have, feature dedicated, exclusively for, such scenarios, right? So in that sense, I'll add the rotating domain moving mesh feature, right? And here I'll select all the domains that are rotating. So here it will be the rotor, the air domain, right, in the rotor, and all the magnets. So these are the rotating components. And the rotation type, you need to define it. So I'll specify a rotational velocity with a general angular velocity, right? I'll give a rotational velocity of 2 times pi. So this is essentially one rotation per second or 60 rotations per minute. So this is the angular velocity. All right, so we have built the mesh. And in the time-dependent study step, we'll define the output times as well. So I'll select the number of values. So start time is 0, end time is 1 second. We'll do the time-dependent analysis for 1 second. And I'll add 51 values. So the time stepping is 0.02 seconds, right? It starts from 0 seconds. There is a time step of 0.02 seconds until 1 second. So to calculate the losses, right, I'll be adding a time to frequency loss study step as well, right, under the different other study steps. So time to frequency losses. And so let the time interval be user defined. Start time is 0 and end time is 1 second. So here in the time to frequency losses study step, you can also define the number of harmonics that you would like to consider for the losses, right? So we can, here we consider 6 harmonics for the computing the study, computing the losses. All right, so after that, we'll finally compute the study. And so before, all right. So it starts computing, right? So in the interest of time, so it'll probably take around 3 to 4 minutes. In the interest of time, I already have a solid model. So I'll just showcase that. So once the study is done, you can visualize the results in the results and visualization section. So first, what we can do is we can extract the losses, right? So for that, what we can do is under the derived values, can go for surface integration option. Right? So this rmm.qh is essentially the volumetric loss, expression, right? So which is essentially as a unit of watts per meter cube. So, and we have, done a surface integration operation on that. And assuming an axial length, axial length of the motor as 80 mm. So we have multiplied the axial length and we are getting the final loss in the form of, watts. Right? And that is essentially 0.5308. So what I'll do is I'll quickly add that feature just for demonstration purposes. So if you add the expressions under the component, you have the different heating and losses rate. Under that, you have the rmm.qh. So there is the volumetric loss density in watts per meter cube. Right. I'll add that. But since this is a surface integration option, so the unit is in watts per meter. And we will multiply that with the 80 mm axial motor length. And it automatically changes the unit, right, from watts per meter to watts. Once you click on evaluate, you'll get the loss, right? 0.53 watts is the total loss. All right, so the cycle average losses is essentially, the same parameter. right? You can see the surface plot as well, the RMM.QH in watts per meter cube. You can see the different, you know, the losses at different parts of the geometry. So here, this is the magnetic flux density, right? So this has been taken from the, time-dependent study set. So you can start off on the first time point. You can see the time points here, starting from the 0 seconds. You can go to the subsequent time points, 0.02. You can also visualize the rotation of the rotor here as well. Right. You can also, create animation out of these, time varying plots, right? So I've already created the animation here. So using these plots, we can make some observations, right? So the time average values of flux density is low in some of these regions, as you can see, right? The green and the blue regions, right? So, and removing some material in that region will not affect the torque produced by a lot. And so in some of the regions, I mean, in some of the corners here, there is a very high value of flux density, right? So, and this can be probably be reduced by providing fillets in this region. So, I mean, these can be some of the inferences that can be made by looking at the different plots, right? And in the rotor part, you can see that the magnetic flux is almost close to zero if you look at the contour, right? So from this, probably, the magnetic material can be scooped out or be replaced by a cheaper material. So, I mean, these are some of the inferences that you can draw out of the different contours. So also using the 1D plot group, you can plot the, three-phase voltage as well, right? Here you can see the voltages from the three winding phases here, right? So since this is a 10-pole magnet configuration, you can see 5 peaks, right? 1, 2, 3, 4, and 5 in the graph here for 1 second. So due to one rotation, there is so the flux interaction happens 5 times because of 10 poles. Right? Essentially 10 magnets or 5 poles. So hence you can see that effect as well. So if you go to the global plot, here you can see the three expressions which represent the three phases of the bindings, right? So you can add these expressions from the different expressions out of here. So we have the different windings parameters as well. It can be winding phase current, phase resistance, phase voltage, line to line voltage, etc. So if you remember, we added the torque, calculation feature. So here I plotted the, the torque as well. So this is essentially the cogging torque. So here we have not excited the stator coil, right? So you can see that the average torque is close to zero in this case. So this is essentially the cogging torque. I mean, basically due to the resistance to the magnets, right? Due to the induced eddy currents here. Yeah, so with this, we have come to the end of the demo. So this was just to give you a brief, look into the various capabilities of COMSOL when it comes to the modeling of motor. You can also have very detailed models as well. You can also have detailed 3D models as well. As it was explained in the different user stories, right? So our users have performed very detailed electromagnetic, multiphysics analysis as well, structural CFD, and they have seen very positive results, business-wise as well. Yeah, so I think now we can move on to the Q&A section. So Yeah.
Sure. Thank you. Thank you so much, Sharath, for that detailed presentation and the demo. And we have got quite a number of questions here with us. So I'll start off right away, because I think we are already running behind time.
Okay. Yeah, sure.
This is the first question from Mr. Sachin, and he wants to understand, are there any hands-on training available on this subject by COMSOL, and how is the correlation of the COMSOL simulation with real-world tests?
Yeah, thanks for the question. So yeah, we have very detailed training sessions as well that we can arrange with our customers. So we also have different strategies where we can also have POC. We can create proof of concept models for the customers as well. So, and we also have different validated models in our application library. Yeah, sorry. We also have different validated models in our COMSOL's application library, right? And these are validated models, and so yeah, so essentially, yeah, so these are real-world validated models that you can find in our application libraries. Yeah.
Okay. The next question is from Mr. Sanjay Sapru, and he wants to know how to improve motors efficiency and while the electric vehicle is running in monsoon season, and how the rainy season can impact a motor's performance.
Yeah, so that is a very good question. So yeah, for that purpose, you can always carry out, the electromagnetic analysis coupled to the, flow analysis, CFD analysis as well, and heat transfer analysis. You can check the various, sudden, temperature gradients that can be caused due to the various splashing effects, right? You can always analyze that in COMSOL. Yeah, so when it comes to the the multiphysics simulation that you can do, the capabilities are the possibilities are endless, I should say. Yeah.
Okay. The next question, where do we generally get to know about the number of poles for the motor, and can that be understood from the CAD data, or what is the source for that?
Yeah, so the models that we have in the part library, right? As I was showing you before during the demo, you can define the different the number of stator windings as well, or you can even define the number of magnets as well according to your requirement. Or if you are using any third-party, CAD software, you can always use our COMSOL's proprietary live-link feature, and you can do, coupled simulations. Right? So once you make any geometric changes in third-party CAD tool, that will be automatically reflected in COMSOL and vice versa. Right? For example, if you do any optimization study of the motor, the optimized geometry will automatically be reflected in the third-party CAD tool as well, if you're using a live link license for that
Right.
particular third-party tool.
Okay. And a related question to that, Sharath, is that, is the COMSOL web version software available for free with some constraints for users to check the UI and solve some of the basic industry problems and gain some confidence before, buying the tool completely?
Yeah, definitely, sir. You can do that. So what you can do is, if you can get in touch with one of our sales representatives, right? And so he or she will gladly provide you with a trial version of the COMSOL, and that trial version will have all the capabilities, right? So you can make use of that for, I mean, so the typical trial, duration is for 2 weeks, but depending on your requirement, so that can be extended as well. So you can always get in touch with our salesperson, and yeah, we can figure out something.
Okay. Is it possible to convert a 1D model from COMSOL into a 3D motor model?
Yeah, we have few features to extrude the solution to either 2 dimension or 3 dimensions. But yeah, we'll always have to look at the the particular case, and probably we'll be able to comment accurately after looking at that particular case.
Okay. And you talked about loss calculation in your presentation. So does loss calculation calculate magnetic losses due to harmonics as well?
Yeah, sure. So in the time to frequency losses of the time step that I added, right? So that essentially takes care of the harmonics as well.
Okay, right. And lastly, does the software also include steel properties from different suppliers?
Yeah, I mean, so we have collaboration with a few of the suppliers, but you can always import your own material properties as well by creating a blank material, and you can define your properties.
Okay, right, right. So there's another question from Mr. K. Siva. If we model in software, then can we extract the product drawings? Are you able to understand that question?
Can you come again, Mr. Man?
If we model in software, then can we extract the product drawings?
So yeah, so essentially you start off with the drawings, right? Using the drawings, you create the CAD parts, and then using the CAD part, you create the simulation model. So
Okay.
I think that's what the question is about.
Okay. I hope, Mr. Siva, you've got your answer from Sharath, because the question is not really well worded here. Okay, so there's another question. How different are all simulation software? Okay, so I mean, how different are all simulation softwares in practical and theory?
So simulation, there is always some approximation in simulation, right? Because they're all based on numerical methods, and numerical methods are essentially, they involve some form of approximations.
Mhm.
But yeah, that's the reason we have validation models, right? So we validate the simulation models with the experimental models, and then we come to the conclusion that these values are usable, right? That's how we go about it. So, but yeah, of course, we can't comment on any other simulation tools. But yeah, COMSOL has a part library which has validated models.
Okay.
And I think the biggest validation is the usage by the industry leaders, right, of COMSOL. So we have, industry leaders such as Volkswagen, Bosch,
Mhm. Mhm.
Boeing, among others, that are users of COMSOL.
Okay. Right. I'll take the final question here. Is there possibility of co-simulation of COMSOL with AVL Cruise, GT Drive, and MATLAB numerical models?
Yeah, so we have the proprietary LiveLink, technology, and you can use that to do co-simulation with MATLAB and Simulink. Right? So yeah, you can do co-simulation with Microsoft Excel as well. Right? And yeah, so these are the three possibilities when it comes to co-simulation.
Okay. Shard, I'll take just one more here from Mr. GK Venugopal. How to calculate synchronous speed with respect to torque and load of a motor?
Uh, Sorry, man, can you come again?
How do we calculate the synchronous speed with respect to the torque and load?
Okay, so yeah, so in this case, we did not give any excitation current, right, in the multi-phase winding feature. So here we essentially the model it as a generator, but yeah, you can also do that. You can extract the synchronous speed as well. So there are different features under rotating machinery magnetic, and yeah, probably this probably needs a very detailed approach to answer this question. And so we can probably raise a support request for this question, and we'll have a detailed response to this as well.
Okay. Okay. So, Sharath, I think we've answered most of the questions here, and I think we just have one more poll question. So, if I can ask my backend team to launch the last poll question that we have. Yeah. So, attendees, if you could just take your attempt at this, answering this poll for us, and then we'll go towards ending this session. So thank you, Mr. Sachin, Mr. Karegoda. I think we're getting some very positive feedback here, Sharath. I mean, people are liking the presentation and they've really gotten some good insights from it. So for whoever who wishes to still engage later on after this webinar is ended, We will have this recording of the webinar on the Autocar Professional YouTube channel. So you can go there and, in a couple of days' time, you should be able to see this webinar posted there as well. And I think it's time to close this session now. We've already run out of time. So thank you very much, everyone, for logging into this. And thank you so much, Sharath, for giving us your time and taking us through your detailed presentation. Thanks a lot.
Yeah, thanks, Mayank, and thanks everybody for your interest in today's webinar. Thanks.
Yeah, thank you.